This lecture marks a turning point in our course, one in which we're going to change our focus, shifting away from the structures of molecules themselves and toward how they can be changed from one material into another. We've covered the structure of the atom and how those atoms are connected in molecules through chemical bonds. But today, we're going to be making a change, quite literally. The topic of this lecture is chemical reactions, those processes in which chemical bonds between and among atoms are broken, formed, and rearranged to change one material into another. We've already flirted with this topic a few times. For example, we learned how Lavoisier was able to convert water and iron into hydrogen gas and iron oxide, or rust. And we looked at the Lewis structures of oxygen and ozone, which can be interconverted in bolts of lightning or high in the upper atmosphere of the Earth. But in this lecture, instead of being a footnote, these transitions from one material or set of materials to another are going to be the star of the show. So let's start right at the beginning. What defines a chemical reaction? In short, a chemical reaction is any process that results in the breaking, formation, or rearrangement of chemical bonds. Now, this definition comes with some implications, so it's best if we take a moment and lay these out by discussing first what is not a chemical reaction. Remember that chemical reactions must involve the breaking, forming, or rearranging of chemical bonds. So, processes like melting ice or boiling water are not considered chemical changes. During these kinds of processes, the bonds within the molecules are actually unaffected. Now, H2O molecules can be a part of solids, as in ice, liquids, as in liquid water, or gases, as in steam or water vapor. But the molecules making up each of these materials have exactly the same structure. Two hydrogen atoms bonded to a central oxygen in a bent geometry. So, changing ice to liquid water or liquid water into steam does not count as a chemical reaction. In fact, we call changes like melting and boiling physical changes in order to distinguish them from chemical changes. And we'll investigate these types of changes in a lecture all their own. Additionally, processes that change the identities of atoms themselves are also out. Radioactive decay that causes a uranium atom to convert into lead can't be considered a chemical reaction by our definition because the element's identity itself is changed. Nor can we classify the fusion that goes on in the sun as a chemical reaction in nature because smaller atoms are being combined to create new elements. For example, two hydrogen atoms combining to form a helium atom. Again, atoms are changing their own makeup in this situation. So we would call this instead a nuclear reaction. Now, chemical reactions can be thought of as shooting the gap between physical changes and nuclear reactions, at least in the sense of scale. Physical changes involve the separation or conglomeration of intact molecules, and nuclear reactions involve separation or combination of atomic nuclei. But chemical reactions take place right between that at the bond level. They happen when the electrons holding molecules together relocate themselves, breaking old bonds and forming new ones. Molecules themselves are pulled apart or conjoined without disrupting the nuclear structure of each atom that's involved. And when this happens, we call what we begin with starting materials, reactants, or sometimes reagents, and we call what we get out of the process the product of the chemical reaction. Now, this definition may seem a bit narrow, but processes that fit this mold are going on all around us every minute of every day. The batteries powering my microphone here in the studio are undergoing a chemical reaction right now. Clipped to my belt are two small canisters in which certain chemical reactions are going on. For example, the reactant zinc is being slowly converted into a product, zinc oxide. Now, this chemical change does not alter the identity of the elements that are involved, but it does change the charges on ions and the bonds that are holding them all together, for example, in that zinc. Now, as a bonus, it allows me to tap a little bit of electrical energy, and that keeps my microphone running and hopefully keeps you learning. Now, outside of the studio, carbon dioxide emissions from vehicles and biological sources are reacting with water in the air, and that's becoming carbonic acid, a weakly acidic product that makes rainwater slightly acidic. At home, in your favorite bottle of wine, a compound called sodium metabisulfite is breaking down slowly into sodium bisulfite, an ionic compound which is toxic to the naturally occurring bacteria in wine that want to turn it into vinegar to support their own biological needs. Tarnished silverware can be cleaned using aluminum foil under the right conditions, under which silver sulfide and aluminum react to become aluminum sulfide and pure silver. Take the example of steel. That's a crucially used commodity in commerce and construction. But after molding it, though, it commonly has a tough outer scale of iron oxide, and this layer is usually cleaned using hydrochloric acid in a chemical reaction called pickling of the steel. All of these processes constitute chemical reactions because the bonding of atoms is changing. Whether we're building molecules up, breaking them down, or modifying them, they all meet that crucial criterion of bond alteration. So when chemists want to make notes about a reaction or discuss their reactions with their colleagues, how can they do this? Well, typing out a full description or giving a verbal depiction might be cumbersome or confusing, even to a well-trained chemist. So just as we have systems for depicting the molecular formulas or Lewis structures of a compound, we also have a shorthand system we use to convey the conversion of one set of compounds into another. So let's take a quick look here at a generic way of writing out a chemical reaction that is used by chemists to convey that recipe and combination of materials that leads to chemical reactions. Now, a generic chemical reaction can be written in essentially this way. Now, I've got a coefficient for everything involved, right? My reactants or reagents are on the left-hand side of my equation, and you'll notice that they each have a coefficient of x, right? So x sub A for reagent A, x sub B for reagent B, etc. And the same is true for products. I have a coefficient telling me what each of those products, or how much of each of those products will form. I will also very frequently be including the phase. Now that means, is it a solid, a liquid, a gas? Is it dissolved in solution, etc.? So a lot of times it's very important for us to acknowledge the phase of matter, and we'll see why that is as we continue through the course. But for now, let's take this recipe here, this generic reaction, and use it as a template to write out an actual reaction, one that we're going to study in depth. Now let's consider a very real reaction. The combustion of propane. This is a reaction that we all benefit from. Whether it's your barbecue grill or your furnace at home, you're combusting propane most likely to create that energy that you use. So, obviously one of our reagents is going to be propane. C3H8 is the molecular formula for propane. Any combustion reaction will involve oxygen, of course. And we're going to create two products from that combustion. The first of which is carbon dioxide, and the second of which is water. So far we've indicated the materials we'll start with and the materials that we'll be concluding with. But we are leaving some information out. For example, is that water going to be a liquid or a gas? Right? Is that carbon dioxide going to be a gas, or will it be dissolved in solution? There are a number of questions that are still left open by simply writing out this recipe. So let's add some more information. I'm going to carry this reaction out completely in the gas phase. So I'm going to put a gas notation of G on all of these reagents and products. So now I know that I'll be dealing with propane in the gas phase reacting with oxygen gas to form carbon dioxide gas and water vapor. But the question still remains, how much of each? Right? How much propane will react? How much carbon dioxide will form? And to indicate that, we're going to use those coefficients. Specifically, when we react 1 mole of propane gas with oxygen in combustion, it will consume 5 moles of oxygen. And in doing so, it will produce 3 moles of carbon dioxide and 4 moles of water. So this is a completed chemical reaction in which I know not only the identities, but also the phase and the quantity of all the reagents and all the products that will form and be consumed. So this is a shorter-hand notation way of showing this big fancy reaction here that we'll be playing with a little bit later. Again, 1 propane reacts with 5 oxygens to form 3 carbon dioxides and 4 water, all in the gas phase. So a chemical reaction is something like a recipe for changing a set of ingredients, which we call reactants, into a finished dish, which we would call a product. At least in the sense that we know how much of each reactant combines and just how much product they will create when they do. But there's more to a recipe than just a list of ingredients, right? They often require that we combine the ingredients in a stepwise fashion. Think about another familiar process, like building a table. 4 legs and a top have to be combined. But unless you are a very talented carpenter, it's not going to happen all at once. The essential parts will come together to form intermediate constructs. For example, you might first form a table with only 1 leg, which itself comes together with yet another leg to form a table with 2 legs, and so on, until the table's complete. So in a 4-step process with 3 intermediate states, you finished your entire project. Chemical reactions often follow the same sort of trend, taking place in steps with intermediates forming and reacting further as the reaction proceeds. Now, we call this more detailed description of a reaction its reaction mechanism. Now remember that the last example we looked at was the combustion of propane, where we assumed that the reaction all took place in 1 step. But that's not really always the way that reactions happen, and we can demonstrate this using a fairly simple chemical reaction here. We're going to react 2 moles of NO gas with 1 mole of oxygen gas to form 2 moles of NO2, nitrogen dioxide. But this reaction doesn't take place in a single step. It takes place in a stepwise fashion. So I've written a sort of a concise synopsis of the reaction, but let's look at it in a bit more detail here. In this case, I've written the reaction as though 2 moles of NO and 1 mole of O2 simply collide and come out the other side as product. Wouldn't that be easy? But that's actually not what happens. Instead of having all 3 molecules collide and react simultaneously, there's a stepwise process to building it up. So let's look at this reaction again, but let's consider its actual mechanism. And the mechanism of this reaction, the first step is actually the reaction of those 2 moles of NO gas to form N2O2, which is an intermediate. This is going to react further after the fact, but we have to acknowledge that it forms in the reaction. So those 2 moles of NO gas are going to react with one another to form the intermediate. Next, the intermediate itself is going to react in a subsequent step. So here 2 molecules have collided to react, and now we're going to take that intermediate and start a new step with it. In this case, the intermediate will react with the remaining reagent, the oxygen. These 2 molecules will collide and react, creating our final product. Now, there will be many cases as we go forward where it's going to be really important to acknowledge this. So here I have 2 elementary steps which combine to form the overall reaction. If I cancel my intermediates out and then sum the 2 processes together, you can see it's the same reaction in the same notation. But from time to time, when it's important to demonstrate the mechanism, we're going to have to break these reactions down into those steps. Reaction mechanisms are going to come to bear on some very important subjects in chemistry, subjects that we're going to investigate a bit later in the course. But for now, let's switch our mode of thinking back to overall chemical reactions, just thinking about starting materials and products. Now, with the vast library of substances that can potentially be interconverted at the chemical level, it should be easy to see that we will never run out of new reactions to study. In fact, the sheer number of possibilities might be a bit overwhelming to the uninitiated. In truth, it can be overwhelming even to the highly trained. So chemists have devised ways to categorize chemical reactions. By doing this, we help ourselves to better understand them by making us reflect on their similarities and differences, thinking of all the amazing reactions that we study, not as isolated cases, but in more basic terms. So now we understand how to represent a chemical reaction in a condensed, concise way. We also thought for a bit about how complex mechanisms might be hiding behind those simple recipes for chemical change. Now let's spend the rest of our time today trying to classify some of the reactions that we've just discussed. There are many ways to classify chemical reactions, but the most general system consists of 4 simple types of chemical changes. Those are synthesis, decomposition, single displacement, and double displacement. Now, synthesis takes place when 2 or more smaller reagents combine to form a single larger product. Decomposition can be thought of as the reverse of synthesis, or a process in which larger starting materials are broken down into smaller and more numerous products. Our third class, single displacement, can sort of be thought of as a combination of synthesis and decomposition, in which one reactant replaces part of another molecule, liberating that which it replaced. And finally, the fourth class is double displacement, sometimes also called metathesis. In this reaction, 2 or more reactants exchange a portion of themselves with one another. We've already mentioned one of each of these types of reactions during this lecture, so let's go back and try to classify those examples now. First, there is synthesis. Synthesis reactions build larger molecules by combining 2 or more smaller reagents together. And an example from today's discussion would be the formation of carbonic acid from water and carbon dioxide. This environmentally critical reaction is a synthesis because it combines 2 molecules, the water and the carbon dioxide, to make one larger compound, carbonic acid. Next, decomposition. The breakdown of sodium metabisulfite into sodium bisulfite would be classified in this way. This is because one larger reactant, the sodium metabisulfite, breaks down into 2 smaller products, the sodium bisulfite. A single displacement occurs when you give silver sulfide a chance to react with aluminum metal. The aluminum takes the silver's place in the ionic compound, while the silver becomes pure metal. Essentially, one pure material has switched places with the other. The central reaction used in the pickling of steel is a perfect example of a double displacement reaction, because iron in combination with oxygen reacts with hydrogen in combination with chlorine to form products in which both species have exchanged one of their partners. Of course, there are many ways to consider and characterize reactions, and this system of thinking is just one of them. From time to time, we'll learn to think of reactions in new ways, reclassifying them in new categories. But for now, we're going to need to change gears and learn an important skill that's going to come in very handy when it comes time to use these reactions as we've learned to write them. Now, chemical reactions, when written out in the style that we just learned, can be used as a tool to design and even predict the results of chemical reactions that we can use in the lab, manufacturing plants, and elsewhere. But we're not quite ready for that yet. There's still a disconnect that we need to address. You see, reactions are written out using coefficients to indicate numbers of moles of each reactant and product consumed and formed, respectively. But we're out to use chemistry in the real world. We're researchers, manufacturing technicians, and chefs, and they don't count out molecules. The idea is kind of absurd, right? Because think about this. How can we count molecules that we can't even see, let alone count enough to be a meaningful quantity? They're so small. So counting a trillion invisible molecules to set up a chemical reaction simply is not how we function. No, we like to measure quantities that can be determined using simple equipment quickly, like mass, for example. But therein lies the question: how do we use a recipe in moles to do business in grams? We have to do some unit conversion. One of the simplest forms of measurement that we can perform in the laboratory is the measurement of mass, weighing objects or samples. So, how can we use such measurements to discuss chemical reactions? Well, we turn to our old friend, the periodic table. The periodic table gives us information about the masses of atoms, specifically about various isotopes of them. Let's take an example that we're very familiar with now, carbon. We know, of course, that carbon has 6 protons. So regardless of which isotope we consider, carbon will always have these 6 protons. But most typically, carbon is an isotope with 12 total nucleons. In other words, it has 6 neutrons in it as well. So when we put these together to form a carbon nucleus, we get a carbon-12 isotope. Now, we all know that there are electrons in the cloud around that, but let's eliminate them for a moment and just consider the nuclei themselves, because that's where the bulk of the mass from an atom is contained. Now, not every single carbon atom in a sample will be a carbon-12 atom. Actually, this carbon-12 here has exactly 12 AMU worth of mass, and it also has about 98 friends out of every 100. So here are 99 carbon-12 isotopes, each of which weigh exactly 12.00 atomic mass units. But what about that other 1%? Well, in nature, that other 1% is actually a carbon-13 isotope. So they would still have, in this case, 6 protons, making them carbon. But instead of just having 6 neutrons, there's actually a 7th one. This gives us our total atomic mass of about 13 AMU. So let's put that nucleus together. Now, I have an approximate mass here of 13.00 AMU. It's actually very, very close to that. So we'll be using that as an estimate for this lecture. And then in the future, we'll discuss why I had to put that approximation sign there. But for now, this is very accurate, plenty accurate for the point that we want to prove. So 1 out of every 100 or so atoms of carbon in a natural sample is carbon-13. So how does that affect the average mass of a carbon atom? Well, we have to use the relative abundances to calculate a weighted average in this case. So the average atomic mass of a naturally occurring carbon atom would be 1.1% times the 13 atomic mass units for carbon-13, plus the 98.9% relative abundance of the 12 AMU carbon-12 isotope, normalized to 100%. And when we run this calculation, what we find is that your average nucleus has a mass of 12.01 atomic mass units. So if we're going to consider the masses of large collections of atoms, say moles worth of them, we want to be sure that we use the average atomic mass instead of the atomic mass of any one particular isotope, so that we know we're calculating things correctly. Now, that may seem like it was a lot of work just to figure out that there was only about a 0.1% difference between the average mass of carbon atoms in nature and those of carbon-12. But consider this. While there are some atoms that are well behaved, like hydrogen, oxygen, and nitrogen, because they have one isotope which is particularly dominant, there are other elements in the periodic table that don't behave so well. Classic examples of these are chlorine, bromine, and magnesium, each of which have non-whole number atomic masses on average. And the reason for this is that, for example, chlorine has 2 common isotopes, 35 and 37, at 76 and 24% abundances respectively. Bromine at 79.9 on average is actually a collection of 2 isotopes, bromine 79 making up about 51%, and bromine 81 making up about 49%. And magnesium actually has 3 commonly abundant isotopes, magnesium 24, 25, and 26. So using these relative abundances and atomic masses, we can calculate the approximate average atomic masses for any element that we choose. So why is that so important? Well, it becomes important when we want to calculate a molar mass. Remember, our goal here is to get to a point where we can use a measurement from the laboratory to start thinking about things in terms of numbers of molecules and atoms. And we're not quite there yet, because an atomic mass unit is actually a very, very small amount of mass. We can't weigh that in a lab. But we can weigh out grams. And we do know that atomic mass units and grams per mole are the same number, because they're each modified by a mole divided by a mole. So let's think about a molecule of methane here. Now, a molecule of methane contains 1 carbon atom and 4 hydrogen atoms. Therefore, a mole of methane molecules will contain a mole of carbon atoms and 4 moles of hydrogen atoms. And now that we know the average atomic masses, we have a way of calculating the molecular atomic mass, or the molecular mass. Let's do that right now. So the molar mass of methane is equal to 1 mole of carbon times its average atomic mass of 12.01 grams per mole, and also 4 moles of hydrogen times its average atomic mass, which is 1.01 AMU, or in this case, I'm using grams per mole. Now, when I do the math here, what I find is that 1 mole of methane should weigh 16.05 grams. Now I have a measurement I can use to relate number to a mass that I can actually measure in the laboratory. Let's try another example here. Let's do propane, a molecule with which we're very familiar. Now, propane, a molecule of propane, has 3 atoms of carbon and 8 atoms of hydrogen. So a mole of propane will have 3 moles of carbon atoms and 8 moles of hydrogen atoms. We can calculate its molar mass, making sure we remember we have 3 moles of carbon times its average mass, plus 8 moles of hydrogen times its average mass. That will give us the total mass of 1 mole of propane gas. And in this case, our calculation tells us that a mole of propane should weigh 44.11 grams per mole. So you can see here that it's becoming relevant. We have to be very careful to keep track of these small changes in the mass due to various isotopes being present, to be sure that we're getting just the right conversion factor to get from grams to moles and back again. Now that we understand how to calculate the molar mass of any particular element or compound, let's apply that knowledge and answer a couple of questions. Specifically, let's answer this question right here. What is the mass of 2.3 moles of magnesium? Now, we know that magnesium has 3 naturally occurring isotopes and therefore has a non-integer molar mass. So our 2.3 moles of magnesium, when converted into grams, needs to be multiplied by 24.3 grams of magnesium per mole of magnesium. Our unit analysis tells us that we've got the correct setup here, and this gives us 55.9 grams of magnesium in that 2.30 moles. So we've successfully traversed that gap, again, between moles and grams. We can also go the other direction. Let's answer another question. How many moles of methane are in 30.0 grams of methane? Well, we have what we need to answer this question as well. 30 grams converted into moles can be done using our molar mass that we previously determined, 16.05 grams of methane in 1 mole. My unit analysis in this case, again, tells me I've got my equation set up correctly, and I can determine that I have 1.87 moles of methane in 30.0 grams. Now we're experts at navigating the disconnect between molar relationships of chemical reactions and the masses that we can actually measure in the lab on a balance. Now, with these tools in hand, our next task will be to use some chemical reactions and our newfound navigational skills to answer some very practical questions about how to set up a chemical reaction to reach a specific goal. So let's summarize what we covered today. Today we took our first small step towards understanding how chemists classify and convey chemical reactions. We discussed how chemical changes are those that take place as chemical bonds break and form. We thought about how some changes take place on too large of a scale, like melting and boiling, which separate intact molecules from one another. Then we zeroed in on changes at the chemical bond level and got down to business. We investigated how chemists write reactions out on paper using a systematic code on which we've all agreed. This code contains the relative number, molecular formula, and usually even the phase of each substance participating in the reaction. And this gives us a detailed description of a reaction with just a few characters. We thought about how some changes can happen in stepwise fashion, sometimes requiring us to write reactions out in multiple steps, known as a reaction mechanism. Then we took a look at how chemists tend to classify reactions using the example of what I like to call the Big Four: synthesis, decomposition, single displacement, and double displacement. Then we put our knowledge to use, classifying a few of these reactions from earlier in the lecture using our system. And finally, we considered the issue of converting grams into moles and back again so that we can move between measurements we take in the real world, like grams, and the coefficients in reactions, which indicate moles. We did this using the molar mass, which can be calculated from the atomic masses of all the atoms comprising a particular molecule. But we aren't done yet. Those coefficients on the reactants and products of a reaction are particularly special and useful. So useful, in fact, that they get their own lecture in our course. Next time, we'll consider this important feature of chemical reactions and use it to answer some practical questions about performing the science of chemistry in the lab.